Hello, this is going to be a really brief guide on what PID control is. Note that because this is going to be a general guide, I'm going to be skipping a lot of the more intricate controls theory. So just note that this isn't an all-encompassing guide. So first, let me describe what PID is. PID stands for proportional integral derivative. It's a controller that is used for getting really precise outputs in real-life systems, which is important because in real-life systems, you get a level of error that you need to account for. What PID does is makes it so that this error is accounted for and you're as close to your expected outcome as possible. The best example I could think of is a thermostat. So for a thermostat, you set it to a specific temperature. And what the thermostat does is heat up the room so that it's about at that temperature. If it gets a little too hot, it shuts off and then waits for the room to get colder. And then once the room is a little too cold, the thermostat will start heating up again so that's about at that intended temperature. There are three main PID characteristics or gains that you need to pay attention to, being the proportional, integral, and derivative gains. You can see them represented here in the transfer function and also here in the system block diagram. So what these gains actually do are represented in this table here. And you can see those different characteristics represented in this graph down here. For a PID controller, you need to tune it so that these three gains get you the system response that you want. And I will demonstrate that in the little demo I have set up. So here is a little MATLAB script that I took from a previous controls class. Over here, you can see our system step response, and over here is where I will be adjusting our different gains. Note that for tuning a PID controller, there's a method that you generally want to follow called Ziegler-Nichols method. There's other ones too, but that's the one that I'm most familiar with. What I'm going to be showing you right now is a very generalized version of that method. So first, what you want to do is start by adjusting your proportional gain. As you can see here, when I adjust it, the system step response changes. What we're shooting for here for this specific controller is a settling time and then also an underdamped response. Specifically for the underdamped response, we want it so that the second peak here is about a quarter of this first peak here. In other words, quarter length decay, I think. So I'm going to adjust it about to my previous value that I had, which is about here. So as you can see, the system is about a quarter right here, as opposed to this peak. An additional thing to note is that we can see that our steady state error is very positive, assuming that 1 is our intended position. For a proportional gain, this is to be expected, but this is generally something we don't want in a PID control. So in order to get rid of this steady state error, we're going to be adjusting the integral gain. So if you can see, when I adjust the integral gain, that steady state error starts to go away, as you can see right here. Note, however, there is a significant amount of settling time here. So we will need to be tuning this a little bit more so that we can decrease that. So that increases it. Decreasing too much oscillation. So we're going to say about 0.15 is fine. An additional thing to note is if you're tuning your different gains and you find that some values aren't working, it might be beneficial to go back to previous gains and seeing if that will help the system a bit more. So we would then follow this process again with the derivative control, but for now, I'm just going to skip ahead and use the values that I found earlier to show you what the tuned system response would look like. So as you can see right here, we have very limited amount of overshoot right here. And then the system gets to a settling of our steady state here at 1 very quickly. This is generally what you want to achieve for any PID controller. So hopefully this helps demonstrate that a little bit better.